Hello, this is an introductory video of the simulation system for Latin America and the Caribbean. This is a product that has been developed by the Inter-American Development Bank for use by its clients in the region in water resources management projects, in exploring water resources issues, or in dealing with a variety of water and water resources management problems. My name is Fernando Miralles-Wilhelm. I'm a lead specialist here at the IDB in the Water and Sanitation Division. And I'm here to present this video in two parts. The first part is a short overview of the general characteristics of the simulation system, its purpose, its applications, and it goes through quickly a case study in which we're applying it now just to illustrate how the simulation system can be used in an actual project setting. The second part of the video is a little bit more lengthy, but perhaps more interesting because we take the simulation system and run it in real time. We look at the graphical user interface. We look at the basins that have been delineated for the entire Latin American Caribbean region. We run in real time the hydrologic modeling portion of the system, generate some results and output. We view them in tabular and graphical format just to show you, give you a sense of how this would run in real time in an actual live setting. So I hope you find this video informational and useful, and thank you. I want to tell you a little bit about the simulation system of hydrology and climate for Latin America and the Caribbean. And this is a little bit of the extent of the domain of the model, and it covers all the basins draining in Mexico, Central America, the Caribbean, and South America. You'll notice there are some basins within the United States. These are basins that are connected hydrologically to basins in Mexico, so we've included them in the basin delineation in the model. The system contains the location and connectivity and direction of flow for all the surface water bodies in the LAC region. It's got about 230,000 delineated basins throughout the region, and just to give you an idea of the average size of the basins, it's 80 square kilometers. The average path of a flow has a length of about 10 kilometers, so this is just average. And it supports hydrologic modeling at multiple scales. And here's a little cartoon showing the extent of the Amazon basin in South America, and a sub basin within that system, and then even smaller sections of it. And it allows to navigate. And I'll show you in the next part of this video, I'll show you a little bit of the navigation capabilities of the system. I want to go through the key features. First of all, it covers the entire LAC region, so it's useful to organize and aggregate scarce data, which is the case with many of the projects that we work on. It's got spatial and temporal resolution that's suited for planning and design of water resources infrastructure at the basin level. So it's a very useful tool for planning purposes. And it simulates basin hydrology driven by climate in a modular, flexible, and scalable way. So it's got a very robust hydrologic model formulation that is able to interact with about any type of climate data model or source. And it's tailored to simulate hydrology and climate problems at all time scales, from near term to intriennial to decadal and beyond. And I'll show you a little bit of a few examples in the next part of this video in a demo. One thing that I find interesting is that the tool has been developed using a web-based architecture, so it runs from a browser-like interface. It's essentially an app. It's a new generation piece of software. The code of the software is open source, and we've designed this tool so that it's community driven, and this opens the door to a potentially very rich development and improvement process for the tool. And this is just an initial release, and it's definitely a unique experience worldwide, so we're looking forward to see how this unfolds. In the next part of this video, I'll show you how we simulate this specific case, but I want to give you the highlights of the first case study that we've done with this model. And this is a basin in northern Argentina. It's the Rio Grande Basin, which is a part of the major Bermejo binational basin in northern Argentina and in southern Bolivia. Here you have the major systems of that basin delineated. I want to show you a little bit of the issues that are there. This basin's got it. It's got many uses, competing uses for water. There are a number of dams that are used either for water supply for cities or towns like San Salvador de Jujuy, which is the major city in that part of the basin. There are irrigation dams, and there are hydropower dams. Some of the downstream of the hydropower then gets diverted for irrigation purposes. So the upper part of the basin has got some pronounced dry season shortages of water. So in the dry season, they run into issues in water allocation, and this is the perfect type of application for a model like this for planning water allocation and especially for planning into the future under stresses such as land use change, climate change, population changes in allocation and these issues. This is a sample output. I'm going to show you this exact graph as output from the model, but this is the graph that we use to calibrate this model with data, daily runoff data, stream flow data for 10 years between 2000 and 2010 in this basin. I'll point your attention to sort of the values of the peak flows, just to give you an idea of where the peak runoff and stream flow generation occurs and how much it is. And in this case, we pulled the climate projection data for the next 50 years, so between 2010 and 2060. In this basin, it was projected that it would experience about a half of a degree C increase in temperature. And this is the simulation I'm going to show you later in the models how to run this, but I'll show you quickly the results. And this is a 50-year simulation, 2010 to 2060. These are average monthly values here, and what you'll see is that if you look at these peaks, 200, roughly around 200 at the most. Some go up to 240 thereabouts. If you compare those, I'm going to toggle back a couple of slides to the values that we had here, which were more in the 320, 40, values. You can see that with that half of degree C temperature increase, the stream flow goes down by about 20%. Okay, over the 50 years, which is that's a concern for these competing uses of water. Okay, so it's kind of interesting how this plays out, and you can do all sorts of analysis. In this particular case study, we ran, for example, projections of annual unmet demands of water, and you can see, of course, that as the stream flow goes down because of that increase in temperature, the unmet demand goes up under a variety of climate input models that were downscaled for this location. And you can do this on a monthly basis. Here you can do the monthly unmet demand, and or you can actually quantify flow duration curves for risk quantification and maybe insurance underwriting. So those are the types of applications that the output of this model can be processed for. Okay, and this is the last slide in this part of the video. I just want to show some other useful applications just to try to understand the range of possibilities of applying a simulation system like this. Anything from water allocation, budgeting, infrastructure, resizing, managing programs, etc. So I'm going to leave this part of the video as that, just to keep the video short. In the next part of the video, I'll show you a live demonstration of the model running. So I hope you enjoy that too. A short demo of the system just to show it to you operating in real time. And so I'm going to fire up the system, and you will see the first thing you'll see is that this runs in a typical platform, GIS platform with layers here on the left. I'm going to load on a base map from Yahoo. It's basically pulling this map off the web. There it is, and I am going to zoom on the coverage area of the system, which is Mexico, Central America, the Caribbean, and South America. So I'm going to do a little zoom there, and let's do that so we can highlight on the coverage area. And so let the base map load again, and Sometimes it takes a little bit to load these layers. It's pulling it off the web, and it also depends on your internet access. I'm thinking of hardwiring these base maps as layers, as hard layers onto to the system. The benefit of doing that is it'll load very, much quicker. The downside of it is that they won't get, updated, which, it depends on how you want to do it, but I think we'll have probably both options. So here you see the coverage area of the system, and what I'm going to do now is going to bring in the delineated basins, and we've broken these down for the time being into two big files. As I mentioned in my previous few slides, the system has roughly 230,000 basins. So what it did now is that it loaded the basins for Mexico, Central America, and the Caribbean, and I'm going to load those of South America. And these two files contain these 230,000 basins. There's about 33,000 or so contained here, and then about 190,000 contained there in South America. So this one's going to take a little bit longer to load. One thing you'll notice is because these layers take their time to load, it's just fractions of a minute, but it's still can still delay things. Rarely you'll be running the whole system with all the basins. So this is something you're not going to be doing every time you run the model. Most likely, as we'll do in this demo, you will be concentrated on a specific area where you're doing your study, your project, and these things are going to load much quicker. So we'll be doing that as soon as the South America layers load. And all I want to show here, it's essentially the area of coverage of the system and how the basins are delineated. So there you have it. So now here, like I said, this is a dense grid of about 190,000 plus basins, and here and to the north of that, Central, South America, Mexico, and the Caribbean is another 33,000 plus, which totals over 230,000. So with that said, I'm gonna get out of this now, and I'm gonna show you. I'm gonna focus in on a specific part of the region where we've done a pilot simulation study for one of our clients, and I'll show you a little bit about how the models run, how you navigate through it, and what results you can get. So I'm going to zoom in into the Bermejo catchment, and I'm going to show it first just to show you a little bit of where it's at. And this is a binational basin here that it covers the southern tip of Bolivia and into Argentina. And so what I'm going to do now is that I'm going to focus on it. I'm going to zoom down to it, and so we can see the basin with. These are here the delineated basins, and this is the Greater Bermejo Basin has roughly a little bit over 2,100 sub-basins that are delineated. And let me reload the base map, and so we can look at the basin delineated within the context of the geography of the region. So let's load that up and see the basin delineated. And for some reason it doesn't want to load up the basin. It'll do it. And like I said, I think I'm going to hardwire these maps into the GIS just so it loads them up, and we don't have to be, it's might be that I have a slow internet connection at this point. There we go. And it's just loading the maps as we go. So I'm going to click on that reload button a few times until I get it. And then what you have here is essentially the delineated basin here of the Bermejo. Goes into the southern part of Bolivia and then Argentina. The city of San Salvador de Jujuy, which is here, and which is one of the focus of our study areas. And we worked on the northern part of this basin, which is a sub-basin within the Bermejo system that's entirely within Argentina. That's the Rio Grande Basin. Okay. What I'm going to do now is that I'm going to zoom a little bit further into it, and I'm going to particularly the northern part of the basin. So I'm going to just do maybe I can catch the whole basin, or at least catch a big part of it within this zoom. And I'm going to show you how we navigate in the system, and that didn't suit me too much. So I'm going to just go into the northern part, and I'm going to show you a few things in navigation. We're going to run the model, the hydrologic model, generate some stream flow graphs, and see how we navigate the system. I think the first thing that I'll do is that I'm going to load up. We have in the Bermejo we have a series of hydrologic gauging stations for stream flow, and I'm going to show you that. Let me load up that layer, and this is going to show where these stations are located, and there they are. And I'm going to bring up a feature of the model that's the navigator, and this is essentially a little dialog box. I'm going to place it there so it doesn't disturb our navigation, and I'm going to select the South America flow lines, just so we're able to show the connectivity of hydrologic basins in this part of South America. So this allows you to do a couple things. It allows you to do navigation upstream and downstream. Upstream means if you select a point, and I'm going to activate this, and I'm going to navigate upstream. If I click anywhere, this will tell me which basins within this system that I'm simulating drain to that location. So you get a little dialog box, and I'm just gonna select one at random just to show you there. And what this is going to do is that it's going to show me which basins are connected upstream to that location. So which parts of the basin drain to that location. And what this is telling me right now is that that basin is sort of self-contained. Basically, it's the basin drains itself. Of course, if you click on one of these stations, and these stations are there for a reason, is because they pick up drainage from other parts of the basin. So I'm gonna pick a basin here, a station here in Embarcación, and I'm gonna click there and see the difference now with the drainage, and it's going to show me which parts of the basin connect upstream to that location. Okay, and then what you can see here now is that this basin drains this entire portion of the basin. So this little basin here drains this area. Okay, and you can do the same. I can go to this other station, Caimancito, and do the same exercise, and so this will show you essentially what's the upstream navigation. Okay, let's see what that turns, and it'll probably be draining another portion of the basin. Actually, I may have clicked incorrectly there. Now, let me click again, right on the station. It might just be that I just did the downstream of it, or a downstream piece of it, and see what we get. And see, now we from this station, we're able to pick up the drainage of all these sub-basins. Okay, let me show you. I'm going to switch gears. I'm going to reset, and so we blank this out, and I'm going to show you downstream navigation. And if you switch onto downstream, now it will tell you, if you give it a location, if you click here, it's going to tell me where that point drains downstream. And this is useful to understand downstream connectivity, to look at patterns. For example, if there's a sediment loading or a nutrient loading, or even a pollution event, where would it be carried by the surface flow in these basins? So I'm gonna again, I click at random at any location, and let's say it doesn't have to be a station in this case, but let me just click like there, and see what it does, just to in a way to understand how the basin drains from that location downstream. And see what this tells you is that this location basically follows this path out of the basin. Okay, all the way out. And I can do the same from anywhere. I'll do the same from uppermost point here in the basin. Let me click right there and do the same exercise and look at downstream navigation. Okay, and again, it's going to show you where this water from that location. It showed it quite quickly, and essentially it's the drainage pattern is very similar. Once the water starts getting downstream in the basin, it all drains out. So we can do that, and we can do this from any location. And if you think about the entire Latin American and Caribbean region, you can do this anywhere. And I'm going to be showing you a few more examples about this. What I want to show you now is the actual model running, not just the graphical interface and the basin connectivity, but the actual hydrologic model running. In order to do that, I am going to run the other module and you'll see, and this is essentially the dialog box for the generalized water loading function, the GWLF, that I discussed previously. And what I have set up here is, I'll show you how the model runs. It's essentially a very simple dialog box. At the bottom of the box, you have the hydrologic parameters, okay? And the GWLF formulation we chose because it's it's very robust and it runs very well at a variety of timescales. And the second reason we did is because it's a very simple hydrologic model. It's got some very simple parameters for for soil type, for land use, and for things like the curve number, and other other hydrologic parameters. But what I want to focus now is the attention is a little bit on the dialog box, and here we calibrated the model with a station with a drainage station that was located downstream of the basin, this is what I'm going to show you first is a simple 10-year run. So this is a 10-year with daily time steps run, and this is the simulation that we use for calibration. So I wanted to show you that, and you can actually input if you need to, and we'll do a longer time series. We'll do later a 50-year simulation to show you the results. And what you can do is adjust temperature and adjust precipitation in case you want to increase or decrease temperature and or precipitation. And so for the calibration run, we ran the data as is with no climate change, but we can actually run a climate change run simulation in a second. So what I'm going to do is I'm going to run this. I wanted to show you how quickly this runs, and essentially the first stage of running, and this run takes like a couple of minutes to run these 10 years at daily time steps. It basically does this caching of base data. What it's doing here, it's assembling the drainage network. It's looking at and remember the Bermejo, this basin's got like 2,000 plus sub basins that are connected. So it's assembling that network connectivity, and then once it does that, it essentially starts sweeping through the 2,100 basins, calculating the water balance for all of them for the 10 years on daily time steps. And so it's going to start doing this in a minute. While it does this, I can actually, it's actually doing it now. So now it's actually just running through the 2,100 basins, the 10 years daily time steps, and it does it very quickly. You can see the counter here looking at, this is the ID of each of those 2,100 basins, so it's done. And then I'm going to show you the results, and the results are given in two forms. In one form is a tabular form that shows some key statistics. So there it is, and the other part of it is graphical. So I want to just briefly show you this. What it has here is for the 10-year simulation. For each month, it'll have the observed simulated average values, and then the difference. And then for each year in the simulation, it shows you the observed versus simulated mean. So it's got annual, and you can show this also. And I'm gonna go to the graphical portion, which is it's going to be a little bit more interesting. And here, what you can see is essentially the comparison between the red. It's the measured values, and the blue is the simulated values. And this was done for calibration purposes. So you can see that for the most part, with the exception of a couple of extremes, we're doing okay. If these are daily values, I can go to monthly values, which are a little bit more useful for calibration purposes at this level, and you can see that the calibration actually is much better. So, what I want to do now is get out of this. I want to show you a projection. So this is a calibration run with data compared to gauge data. And what I would do now is actually change. So I'm going to run now. This was done from January of 2000 to December of 10. So now I'm going to run from January 11, okay, to December of 60. So this is a 50-year simulation, and I'm going to do a temperature adjustment of half of a degree. Okay. The reason I do that is because for this region, that's the projected temperature change from a couple of the climate models that are mostly used by the Centro de Investigaciones Meteorológicas de la Atmósfera, CIMA, in Argentina. So I'm just going to change that. I'm going to keep everything else the same. If you have reasons to change parameters, you can go ahead and do that. And I'm just going to run this. And again, it does this connectivity calculation fairly quickly, and then it's going to sweep through the basins, going through daily time steps for all the basins for 50 years, and then it's going to we're going to look at the results, and I want to show you a couple of things, and so it's still caching the base data. And one of the things that I wanted to note is that even a 50-year simulation like this, and you can time it, it's probably going to take something in the vicinity of 4 to 5 minutes. So this is something that runs very quickly, and if you look at a scenario, so now it's running the entire. So right now it's calculating for all the basins, 50 years, daily time steps, water balance, all the components for each runoff, infiltration, evaporation, rainfall, and change in storage. For all the 2,100 basins, 50 years, daily time steps. Once it's done, you can envision using a model like this in a real time scenario, in a workshop with stakeholders, where people can propose ideas and alternatives, and you can run fairly quickly. And within a half-day workshop, you can probably get a dozen of these runs done with discussions and everything. So it's a very time-efficient solver, which is one of the reasons we picked it. So it's done. I'm going to go again and look at the tabular and look at the graphical output and see what we can find there. And this will show you the time series of flow in that outlet. And you can pick where you want to see your graphs. So it takes. This one takes a little bit longer to assemble the graphs and assemble the tables, just because it's 50 years daily data, so it'll take a little bit. But again, this is the point of the workshop, where people can stand up, go get a cup of coffee, maybe catch up on a chat or on some gossip from your colleagues from an agency. What people do at workshops, you can do here, while the model shows results, and then we can take a look at the output and see how that goes. This is going to take maybe a minute or two longer. We'll see. One thing I can do, just so I don't leave you waiting, is that I can go back to the graphical interface and show you the model navigation in other places, and the software will let me know when this is done. So I'm going to go back to the GIS interface here, so let me go back to the GIS interface. And what I'm going to do is I'm going to get out of the Bermejo, and I'm going to do a little bit of navigation further north. And I've done some live demos of this, and I take questions from the floor. People tell me, well, let's go to Panama, let's go to Brazil. I'm going to show you a couple things that we're going to be working on soon. And so I'm going to center. Oh, it's done. So before I do this, sorry, it's done here. Let me go back, and so here's the tabular format. Okay, I'm going to show you this, and so again here, because we're doing a projected simulation from 11 to 60, there's no data, so there's nothing to compare to. So this part of the system is not as interesting, but the graphical, you can actually see the simulated values. Again, there's no observed, but you can see the simulated values, and you can look at the monthly values. And if you compare these graphs with the graphs that we saw before for the calibration period, what you're going to see is that when you add a half of a degree to the climate over the 50-year period, and this is done in a linear fashion, when that is done, you get an attenuation of these peaks, of these stream flow peaks, both at the daily and monthly values of about 20%. So it looks like the runoff that is generated by this basin, after 50 years with that half a degree increment in temperature, it's roughly 20% less runoff. So this is something that you can use for water resources planning in the basin. We could have played with no climate change, like 0 degree change. We could have tinkered with the rainfall, depending on if we have a projection of rainfall. We could have increased the temperature, augmentation. You can do a variety of things. So this just gives you an idea. And if you look at how long the simulation takes, it's like I said, it was a few minutes. Very practical, very easy to use. So I'm going to leave it at that for the time being, and I'm going to come back to this. And what I want to do now is I'm going to refocus on Central America, Mexico, and the Caribbean, and I want to show you a couple of navigations there, so I guess I have to reload the map and just show you. Well, show you the basins as well. So there's the map, and I'm going to show you the basins. And again, the basins, take a little bit longer to load, and we'll see how this goes. And I'll show you a couple of navigations. So one that I'm interested in is Haiti, because we're going to be using this model very soon there, the system very soon there. So I'm going to zoom in to Haiti, and we can just look at the base map as well as the flow lines and the basins delineated in that network. So this is the island La Española, and this is Haiti, and the bank's work is concentrated in the northern part. We're working on a sustainable corridor along this area with Cape Haitien, and we're also I'm going to zoom in northern part of the island here, and just show you again the base map and the basin delineation, so what you'll see here is the each of these units is a computation unit, and we're doing work on this major basin, the Trou du Nord, and we're also very concerned about the ecological sensitivity of this Caracol Bay, the Bay of Caracol, which is here, and we can do. I'm going to bring in the navigation tool again. This time I'm going to throw it this side, and we can do very similar exercises. I'm going to select the right flow, and I'm going to activate upstream navigation just to show you a little bit of how it works. And what this is saying, if you click on any location here, it'll tell you which basins drain to that location, and I'm going to just click there just to have something that's connected to the bay, and look at the connectivity of the basin. So it appears that this basin picks up drainage from itself, so there's no upstream connectivity, which means that it's pretty self-contained. I'm going to do some downstream navigation now, so I'm going to clear out of this, and I'm going to do some downstream navigation, and you can see. So let's do some downstream, okay? And so let's look now at what happens if there's some hydrologic change in any of these basins. Let's see where these go. And it's going to show me the downstream connectivity of those basins, or of that point that I just selected there. And what it says is that this basin picks up water from itself, and then it drains it down to the coast, not to the Caracol, but to this side. Okay. You can do the same. We can pick out another basin. Let's say what happens if we pick something closer. Let's see what happens if we pick. I might actually reset this so we don't get confused. with the next one that shows. So I'm going to go now with this to see what happens with this basin and how it drains downstream. And this basin just drains straight up to this embayment here. And I was playing with this the other day, and I found an interesting pattern somewhere around here downstream. I'm going to click there and see what that does, and see where do these basins drain. And this was interesting because it sort of goes around, it sort of comes around this way. And so I found that pattern quite interesting. It would be good to calibrate a model here, and hopefully we'll be doing something like that very soon. So that's the navigation for Haiti. I'm going to close out the navigator, and I am going to let me go back to South America just to show you a little bit more of the demo there, and let me zoom in to that extent. And see. Let me show the base map first. So there we go. And let me focus on. We're doing some work in Peru. And Peru's got an interesting major ongoing program in watershed management and integrated water resources management. So I'm going to zoom in Peru and particularly the southwestern part of the country, and it's a very arid part of the continent, and so let me load the base map again before I load the basins. It's a pretty arid part of the continent, and I want to show you a little bit of the basin delineation, maybe some navigation, just to keep the video short. So I'm going to show the catchments that load up here, and this is interesting because it'll give you an idea. And in Haiti you saw it, but here you'll get an idea of the density of these basins. And so look at this. Each of these little units at this scale, it's a significant level of resolution that you're getting here. And here is Lake Titicaca, and so you can actually watch some of the. We can do again the same. We can bring the navigator and I'll do some downstream navigation here very quickly, just to show, just a quick show and tell about how the system is draining. And so let's wait for it to give me the cross, and I can then start clicking, and I'll just show you a couple of downstream navigations. So let's see what happens with basins that are west of the lake. And so if I were to click there, like in the middle between the coast and the lake, see what happens. And so let's see what happens with downstream navigation there. One of the basins that we're working on is near this location of Tacna. Right there is a very arid region. It's the start of the Atacama Desert, which stretches down through Chile. It's a very arid region. Most of the flow, it's groundwater. But it's useful to understand because they do get flash floods. So here, what you have is that the basins are very arid, so there's very little surface basin connectivity. So this is a little bit of what we would expect in a place like this. If the water starts rising, if you get an event, I'm gonna pick on another basin. Maybe I can do a little zoom in just to. You can just zoom in like this. You can capture the town of Tacna and just reload the whole thing. And now we have the basin we saw before. Reload the base map. And okay, so there we go. I'm going to reset this just to make that go away, and we can So restart with this, final resolution. Let me actually get this these catchments right. All right, it's sort of loading the. It's got two components. It's got the basin delineation, but it also has, and I'll actually show it in this map. I'll show it I'll show the. I haven't done my navigator. It disappeared. I think I might have clicked on something. Oh, there it is. Okay. So one thing I haven't showed, and before I do navigation, is just to show you the density of the streams that are digitized in the model now. So these are the catchments that I can actually select. Also the flow lines. This is another layer that I have loaded up, and what you're going to see now is it's the network of streams that are digitized in the system. And you can see those in blue. So this is the sort of the fluvial network there. Okay, I'm going to turn it off because it sort of makes viewing things at this scale might be confusing. But let me just click out of it. Just wanted to show it to you. Let me go back to the navigation piece. So now the little blue network's going to go away, and I'm going to activate the navigation downstream. And again, I'm going to click a basin. Let's wait for it to give me the crosshair so I can locate it and see. And I'm going to do this. I'm going to click here. Okay, so now it's doing its calculation, and it's going to show me the path. And after we do this, I'll finish the demo. I think it might be starting to get a little bit long, and I think I've given you a pretty good idea of what the capabilities of the system are. So let's wait for that to show. And you can see, again, so some of these bases are self-contained. They sort of, this means that the basins really don't connect superficially with others. This means that primarily water infiltrates and goes away. I'm going to click on another, you click on a downstream closer to the lake and see what they do. And I was playing with this the other day, and I saw some interesting flow patterns, but I'm going to do one more, and this is it. Let me click right here, okay, and see what it does downstream. So showing now the downstream navigation here. And once this is done, we'll close out, and I'll call it a demo video. And you can always contact me with questions and comments. This is release 1. So here what you have, it's an interesting pattern because it drains through the lake, which we knew, and then if there's overflow from the lake, if there's further connectivity from the lake flowing down. So that's one interesting pattern that we showed. Okay. Well, I think I'm going to leave it at that. I think this gives you a good idea. I'm going to close out of here and just exit here. I won't save any of this, and that's pretty much it. So I look forward to seeing you. I hope this demo was useful, and look forward to people using this tool. Thanks very much.